Our second thing today is we've got Kennedy in Arm. This is Senior Director of Verification and CPU Engineering. Having previously worked both at Intel and ARM, Scott has been with ARM CPU team for 14 years. More recently, managing verification of all Cambridge-based CPUs covering A, ARM, and M-class profile design.
Thank you very much. Right, so the brief was to talk about some of the verification challenges we have at ARM. It might not surprise you, given that Brian and Joe both previously worked at ARM, that I know them very well, and I might be about to cover some very similar themes. Is that better? Yeah. Okay. So yeah, we've covered some similar themes. I did ask Brian last night if he was my warm-up act, or whether he'd be a tough act to follow. So we'll soon find out, I guess. Okay, so our main challenges are in the proliferation of our market opportunities. I think a lot of people mainly know ARM for mobile phones, tablets, consumer devices, appliances, that sort of thing. But over the last 5 or 6 years, the market really has grown massively. We've pushed our high-end CPUs up into server space, IoT's become a massive market, wearables, all these sort of things. But with all these new markets come new verification requirements. Time to market is still very much a major issue. And there's also that age-old debate between engineering and marketing, where marketing want the earth, and we say we can't deliver that. And they say you need to deliver it, but you need to deliver it in half the time. I did have a little analogy about that, and I ran it past my colleague Chris, and he said, you can't say that. But basically, I'm sure it's an every man or every woman's story at every company. The marketing team want every single feature possible. Engineering don't believe they have the bandwidth to deliver that. And then management say, yeah, make it happen, but make it happen 6 months earlier. So all of these things add complexity to our verification challenge. And specifically in some of these newer markets, there are very different verification needs. The customers care about different things. So in the infrastructure space, things like error code correction or reliability, which are not as important on a smartphone, are absolutely fundamental. If you're playing, this is where I sound old and I say Angry Birds, or I could try and sound cool like my kids and say Fortnite. If you're playing a game on your phone and it crashes and you just have to reboot your phone, it's not the end of the world. If you're in financial server space and the servers crash, that could have a real dollar cost and be quite catastrophic. So the reliability criteria are very different in the high-end infrastructure space. We've had to do a lot of investment in how we verify those specific areas. In automotive, brakes do apparently need to work. Cars should stop when they're supposed to. So all of the criteria we need to go through for ISO certification has added a lot more to the verification challenge as well compared with the mobile market. IoT, some of our very small microcontrollers that might have previously been in domestic appliances are now in wearables. Wearables expect battery life throughout the day, whereas a domestic appliance would be on at the mains the whole time. So again, a lot of redesign of some of our microcontrollers to make them way more efficient. And then, as Brian previously mentioned, security is a major new threat to us all. So all of this adds verification complexity, verification challenges, and all of it needs more compute. So when I started at ARM, we had one data center, and then we built another data center, and another, and another. And then we thought we can't just keep building data centres, and we did what Joe just told us to do, and we moved to the cloud, and then we used more in the cloud, and then we had an even bigger cloud, and then finally someone said, that's costing a lot of money, don't do that. And so essentially we've got to a point where we can't just throw compute at the problem, we need to be much, much smarter. And that is challenging our perceptions on how we do some of our work, and making us think about it in a slightly different way. That we still use on-prem compute, we still use the cloud, but we are going to have to do it in a more studious fashion. So we've been looking at various things that we've been trying to do to think how can we optimize what we actually run so that we can run less but still achieve more. Obviously, this is my little sales pitch for ARM here. We've looked at the architecture of the machines we run on some of the AWS Graviton servers we see in the cloud. We do get better throughput when we run on ARC64 than on x86. Shameless plug over. But we also do a lot of work with the EDA vendors looking at our test bench performance. There's an example that my colleague Neil in the audience is working on with two vendors where vendor A is much faster on test bench A, but slower on test bench B, and the other vendor is faster on the other one and slower on the other one. So we do a lot of work with the EDA vendors to try and understand where we've got performance issues in our code and where they've potentially got performance issues in the tools. And then that's mutually beneficial. We get a better tool, and everyone else in the room gets a better tool as the result of us working with EDA on that. And I'm sure people from other companies all do the same. So we get the benefit of the work you invest in helping make EDA better as well. But there's some very simple things we do. Engineers like to add tests. They don't like to remove them. Even at the end of the project where you're running extremely complex stimulus, you probably still have the basic bring-up tests in your regression. Why? They're never going to find bugs anymore. They're not yielding any benefit. They're just costing time, costing computers to take them out. Another thing we've got in a bad habit of doing over the years is running extremely large regressions, generating so many fails that we can't actually debug them all before we're going to run the next set of tests. So we're trying to build some intelligence into our flow so that when we hit a certain number of failure signatures, the regression just stops. Why keep running? You've got enough to debug. And that links me to one of the other points. Only run enough that your engineers can debug before your next scheduled regression. So if you're running nightly regressions, only run enough that gives you enough to debug the next day. If you're running weekend runs that you want to debug through the whole week, only have enough that you can debug in the following week. Don't run for the sake of running to hit large cycle targets. It's pointless if you can't debug all the fails. We've also looked at bringing in some software principles like unit test. Quite often when you're writing new test benches, the way you test the test bench is you try it with the RTL and then it doesn't work and you go, is it the test bench? Is it the RTL? Which one is it? We're trying to debug our test benches using unit test checks ahead of time so that by the time we introduce it to the RTL, we know it is good. We also are using multiple simulators in ARM because we're an IP company. We're fortunate enough to have access to tools from all three of the main vendors and many other vendors as well. We see real benefit in running two simulators for our main SOAP regressions to really stress test the health of our designs. Especially with system variable constraints, each vendor's tools solve the constraints in a different way. So they will find different bugs. Now that doesn't mean one is better than the other. It just means it searched a different part of the state space at a different time. So essentially, it's almost like having an extra stimulus engine. By running two simulators, on a given code base, we can then see if the second simulator finds anything the first one has not found. So we always mix them in some pre-decided ratio in our longer soak tests towards the end of the project. Towards the end as well, we also try and balance emulation and FPGA. The more we can run on emulation and FPGA, the less compute pressure we're putting on the estate. But there's no point in doing that too early. Sure, as everyone knows, it's much harder to debug on emulation and FPGA than it is to debug at unit level in simulation. And then the one in the middle I've not talked about, and this is the one that we really struggle with a little bit, I think. How do we find that correct balance between simulation and formal, right? If you've got something that you can fully prove with formal, why even run it in simulation? It's fully proven. Now, in reality, we never get full proofs on some of the things we throw formal at. So essentially, we're using formal as another form of bug hunting, but we still need to try and balance that with the simulation needs as well. And part of the way we try and measure this, to Brian's point about data, is we go beyond just looking at standard metrics like code coverage, functional coverage, and pass rate. We actually try and plot our bug curve against the number of cycles that we've ran for any given technique. And we're looking for that nice trend where it flattens out and the gap between bugs gets bigger and bigger and bigger. And that really tells us we're saturating. And when we start seeing that trend, so on the top is a cumulative trend where red, amber, green is effectively the severity of the bug we've found, versus the lower graph is per test bench. We try and look for those saturation trends and those long gaps between finding bugs. So it's about, again, to Brian's earlier point, how we use data and trying to use data more efficiently. What about ML? It's super trendy. Everyone loves ML. It's all the rage. All the cool kids are into ML. We are looking at ML as well, both with the vendors and internally. So we're looking at how we can use all of our data to try and steer how our regressions run and actually steer into areas that we think will be bug rich. So training the regressions to try and establish patterns around where we believe there are issues and make sure we're running regression in the right place. Again, or taking a very basic CPU example, we could run cycles all day long on a basic no-op instruction. It's never going to fail. If we're not actually testing the complex coherency in the memory system, where all the bugs actually are, then we can run cycles all we like, but they're never going to find it. So we need to make sure we use our brains, but also use some intelligence to try and target where we should be verifying. And we are working with the vendors on that, and also building some solutions internally as well that we can run to basically inform how we make our compute decisions. It's not all about automation. People are very important as well. Within our CPU team, we have Sophia near Nice in the south of France, on the top right, Austin in Texas, top left, Chandler near Phoenix, bottom left, Cambridge, bottom right, and we have Bangalore in India. And historically, each of the four teams in the corners have interacted with the Bangalore team because they provide some system testing and top-level testing service. But we've been quite siloed, right? And we've not talked to each other enough. There was minimal knowledge sharing other than on maybe flow-related activities. But in terms of the low-level details, the assumption was, well, we're all working on different microarchitectures. There's not a lot of crossover. We've challenged that assumption. We've challenged the every man for themselves mentality. And we're now working in a much less siloed way. We're actually sharing test bench development across multiple sites. And even when we can't share code, we're trying to have way more proactive conversations about the sort of technical challenges we're facing on projects. We're not doing what we historically did, which was write a post-mortem type document at the end and hope that other people read it. We're being way more proactive in having conversations between our engineering teams. And again, that goes back to the point Brian was making about understanding design root causes and verification root causes. And we're trying to work on that and create a constant dialogue between our teams. So it's not just about automation. I think if we get people thinking in similar ways and talking to each other, that helps massively. So in summary, you need to learn the key differences between existing markets and emerging opportunities. They have really changed. The focus on some of our verification on some specific products. We need to leverage that wider knowledge base, especially when we are moving into emerging markets. If one team are moving there first, then the second team really need to try and learn from the first. Collaborate on shared verification collateral if possible, but if not, create a free exchange of ideas between different teams. And compute efficiency is absolutely key. To my earlier slide, we can't just keep growing and growing. Compute and farm, it just doesn't work. Only run what you can debug. Run valuable cycles. It's about training your data so that you look in the right place. Train regression using ML to target where there's the likelihood of bugs. Train engineers to make sensible decisions on what they should run and when they should stop or when they should not run. And train scripting to optimize the compute resource. Automatically kill your regressions if they're not producing any value. And when I submitted the slides, I think Mike mentioned, if you have any marketing material, can you put that at the end? And if you don't have any marketing material, I know Mike said, oh, it's just some of the other companies do. So then I had to add one, I couldn't help myself. If you are interested in anything that we talked about and you would like to come and see us at home, then they are always hiring.
Thank you,
But you've got Mike to blame for that one.
You mentioned time to market and also you mentioned being conservative of resources, but it becomes very difficult at the end of the project when you have pressure to take out and some define some works or designer go and do some changes. Then it work or it would be some changes. How do you manage at the time to quickly say, okay, there isn't any work because of this business change? Or basically, how you verify the change at the end of the project?
How do we verify what? Sorry, at the end of the project?
So there could be design change, maybe it will work, or it could be changed in this. And we have to verify that change very quickly. So do you add any intelligence in your automation process just to find out, for example, a particular test cases are targeting this area or that area? When you find some work in that area, first you go and look into that.
So are you measuring the success of how different tests have contributed to the verification?
Not how different tests contribute to particular flow or areas, or when you find work or design change at the end of it, or they're very near to take out, you want to run with that.
All right, okay, so specifically maybe like a late ECO or something like that. Yeah, so typically what we do there is if we know that the rest of the design is looking healthy, we will just target a large amount of resource at that specific area. And then run some of our higher level sanity checks, like if it was something like Linux boot or Android or something like that, so that we know there's been no detrimental impact to that change. But yeah, we would, if we know the rest of the design is healthy, we would very much target those areas. We would target the surrounding area as well. We do find that neighbourhood faults are quite common, especially in coherent memory systems. If there's some sort of incident issue, there might be, we might have found one path into that issue, there might be 4 or 5, so we will hunt in that area.
Okay, thank you, Scott. Thank you. Thanks for the question. Thank you. I'm sure we'll have time with more questions, but we'll have time. Thanks, Scott.